Okay, so we want to find out stability of this polynomial, whether it has negative real roots, roots with negative real parts. So we form the array S cubed. We write 1 here. Skip this one, we write 10. After 10, you have nothing. Then you have S squared. For that one, you have 5. Skip 10, you have 40. You will have 2 more rows here, which I will call S to the 1. Let's call this one B1. Well, and S to the 0, let's call this one C1. These will be determined. B1 is going to be, we will divide it by 5 here. The negative of this determinant, which is 1, 10, 5, 40. So it is 50 minus 40 is 10 over 5, which is, this will be 50 minus 40, because the negative determinant, 10 over 5, 10 over 5 is 2. So B1 is 2. This one is 0 because, well, you don't have anything to find out. And C1 is this determinant, the negative of 5, 40, 2, and 0, divided by 2, which is what? Minus 80. 80, but minus is positive, so it is 80 over 2, which is 40. So C1 is 40, this is 0. And we see that all the terms here are positive. So we can say that all positive. So it is a stable system. As a matter of fact, we can find the roots of this in MATLAB and find out that it is stable. Okay.
Hocam, can you scroll up while you were like teaching us the Routh test? You write like in a different way. Could you just scroll up, hocam? Hocam, in the formula of the B1, you just write A1. So isn't it should be a n minus 1 in the, yes hocam.
This should be, yeah, there is an, actually in my notes, there is a mistake. Just a second. It might be, it cannot be A1, sorry, it must be AN minus 1.
Also for
yeah,
B2,
well,
it should
yes.
be n minus 2, right?
It should be AN minus 1.
For the B2?
Huh?
For B2?
For B2, again, it's AN minus 1.
Okay,
it's
hocam.
always like that. Yeah, thank you. Actually, I just probably, because all other terms are like that, I made a mistake there. Sorry, yeah. So we divide it to this one, which is 5. Then we divide it to 2, etc. Okay. So this one is, all the coefficients are positive. So it passes the Hurwitz's test. And also the root array gives us that it is stable. Let's try something else, something similar, but only the last term is different. S cubed plus 5s squared plus 10s plus, instead of 40, now it is 60. Okay, the same thing, s cubed, s squared, s to the 1, s to the 0. So we have 1 and 10, 5 and 60, B1 and C1. These are zeros, we know this. B1 is equal to 5. So it is 60 minus 50, negative of 60 minus 50. Over 5, which is 50 minus 60, 10 over 5, which is minus 2. Okay? So B1 is minus 2, and C1 is minus 2 is here. 560 minus 2 is 0. What do we get here? Minus. What do we get? I don't know.
60 hocam, I think.
Huh? Is it
Isn't it
positive
plus
60?
positive 60, I think.
Positive 60.
Yeah. Minus. Yeah, it's complicated.
Minus positive hocam. Between the brackets it's minus 120.
Yeah, minus, just a second. 60 times minus 2, but there is this is plus. Too many minuses, and it gets confusing. Just a second.
The
This
minus
a
is
minus.
outside.
There is another minus.
Minus
60
120.
times minus 2 divided by minus 2. 4 minuses makes a plus 60. So it's 6. Yeah. So first of all, you have this one is now negative. But there is another thing. There are, first of all, it is unstable. It's obvious that this is unstable because there is a negative 1 here. But this gives you another information. There is one sign change and there is another sign change. Positive to negative, negative to positive.
Hocam, actually, it is going to be minus 60 because there is 3 minuses.
No, there are 4 minuses.
We also subtracted. Okay,
Yeah.
sure, yes.
Unstable with 2 poles with positive real parts. Okay. So we find that this system is unstable with 2 poles with positive real parts because there are 2 sign changes in the root array as we see. So actually, just a second, let me show it to you. What is that? For example, D equals the first one, 1, 5, 10, 40, Let's look at the roots of this one. As you see, these are all negative, okay? Whereas if we look at the second one, this is 60. If you look at the roots, now the two roots, which are complex conjugates, have become positive, okay? So the first one is has stable roots, whereas the second one has unstable roots with two unstable roots, as you see. Okay, and let's close this. Let's share.
Hocam,
Yes.
what if all of the numbers in the first column are negative? What happens then?
Well, it doesn't happen actually. You know, you cannot have that as far as I can see. It can only happen if all the coefficients are negative, I suppose. But if all the coefficients are negative, you can just make them all positive by multiplying with a constant number or something, and put it in the
So that
numerator.
doesn't change anything.
It doesn't change anything.
So that doesn't change anything.
Yeah.
Okay. And Hocam, one more question. The number of sign changes is the amount of positive real parts, like the number of poles with positive
Yeah,
real
I
parts, right?
will write this down. Just a second. Number of
Okay, Hocam, thank you.
sign changes in the first column is equal and positive real parts means unstable, okay? Another thing is, if you have a second order system, let's say D of S is a trivial example. Let's say A0 S squared plus A1S plus A2, let's say. What is the root array for this? This A terms, we don't know yet. A0, A2, S to the 1 is A1, and this term is, there is none, so we put a 0 here. There is S to the 0. Here we have, let's call this one B1, which is equal to A0, A2, A1, 0, negative, divided by A1. It is minus cancels. This is A2, right? So the first row is A0, A1, and A2. The first column, sorry. First column.
Hocam, isn't it A2 then A0 in the S square part?
Huh?
Isn't it? Sorry, okay, I get it. Sorry.
No, so this one, and the conditions for stability, this is always stable if A1, A2, A0 are all greater than 0 or less than 0. Actually, all of them must be the same. Okay. So second order systems are stable if their coefficients are all positive, which means that the Hurwitz test is also sufficient. Yes. Let's try a more difficult example. S to the 6 plus 4s to the 5 plus 3s to the 4 plus 2s cubed plus s squared plus 4s plus 4. Okay. It passes the Hurwitz test. Let's say passed. Because all the coefficients are positive and they are non-zero. Even, you know, you cannot have 0. Now we have to form the root array, which will be a big one this time. So s to the 6. We'll start with 1, 3, 1, 4. S to the 5 is 4, 2, 4, and 0. Okay, these are obtained from the term. Now we have s to the 4, we go like this. We take the negative determinant of this, 12 minus 2, 10. 10 divided by 4 is 5 over 2, right? This one, it is 4 minus 4 is 0, divided by 4 is 0. This one, 4 times 4 minus 0, divided by 4 is 4, and 0. It's cubed now. We take the determinant of this, which is 2 times 5 over 2, minus 0, divided by 5 over 2. This is 2, if I'm not wrong. Now this one, 4 times 5 over 2, which is what, 20 over 2, which is 10. I don't know, this becomes, we are doing this one. 4 times 5 over 2, 20 over 2, 10. 10 minus 16. 10 minus 16 is what? 6.
Minus 6.
Minus 6. Minus 6 divided by 5 over 2, which is what? Minus 6 divided by 5 over 2.
12 over 5.
12 over 5, right?
Yes.
Okay, what about this one? This one, this is 0. 0. And this is 0. So s squared now. Well, what is this? Uh, 2 times 0 is 0, minus this one, which is what? 6 minus 6, no, 6. 6 divided by 2 is 3. Interestingly, we get a positive number. Okay, how about this one? 4 times 2 divided by 2 is 4. 0, 0. S to the 1. Everything goes well, it seems, but unfortunately, it will break down here. It will be 12 over 5. This is negative, to negative 36 over 5 minus 2 times 8 over 3, and the result will be minus 76 over 15 for some reason. This is 0. These are zeros. The last one is s to the 0. It will be 4 times minus 76 over 15 divided by minus 76 over 15 is 4. So these are zeros. So it looked like it was going to succeed almost, but we have 1 and 2 sign changes. And this one is negative. So this polynomial is unstable with 2 poles with positive real parts. Okay. As we see, well, we saw the mechanics of using the Routh criterion, but we didn't succeed. Actually, you can try this on, find the roots of this on MATLAB and see that there will be 2 roots with positive real parts. Okay.
Hocam, may I ask something?
Yes.
Can we do this, how can I say, calculations to backwards? Like, can we first choose a stable system? Then, like, I just want to ask in real life engineering problems. So we just first make a system, then we examine the roots. And
That's what we do usually.
in the end, if we find unstable system, we just need to go back and define a new system or change the system until it becomes stable.
Well, kind of, but I'll give you I'll give you an example. You have usually certain parameters you can play with. Okay, like gains or the controller parameters. You have to change them so that the system remains in the stable range. I'll try to give you an example now. You have control over certain parameters of your system. You don't have control over your real system, but you have the control over your parameters. So let me give you an example of a control system here. Control system, let's say. A simple one, but it illustrates the idea. Let's say this is the reference input. Let's say that the controller is just a simple gain of k. Okay? The k is unknown. And our plant is, let's say, 1 over s plus 1 cubed. For some reason, I selected it this way. And this is y of s. So this is plant system. This is the controller. The system, the closed loop system between input R and Y, the closed loop transfer function T of S, which is Y of S over R of S, is, as you know, it is K times 1 over S plus 1 cubed divided by 1 plus K times 1 over S plus 1 cubed. Okay. Kg times Kg divided by 1 plus Kg. Okay, as you might remember. Now, if you do this, you are going to get the following: K over, if you equate the numerators, denominators, etc., s cubed plus 3s squared plus 3s plus 1 plus k. So the denominator of our closed loop transfer function is the following: s cubed plus 3s squared plus 3s plus 1 plus k. K is a variable parameter. It can change. Okay, and we can change it. We want to find the range of k so that the closed loop system T of S is stable, for example. Find the range of k so that the system is stable. What do we do? First of all, we look at the parameters. The parameters are all positive except the last one. K should be greater than -1 in the first place. We can see that, but let's skip that for the time being. Let's form the root array. S cubed is 1 and 3. S squared is what? 3 and 1 plus k. S to the 1 is what? 9 minus 1 plus k. 9 minus 1 plus k is 8 minus k over 3, right? Minus k over 3, this is 0. S to the 0 is 1 plus k. So 8 minus k divided by 3 must be greater than 0, which means that k must be less than 8. That's one condition. And 1 plus k must be greater than 0, which means that k must be greater than -1. So the condition for stability is this. These two things combined is -1 should be less than k, less than 8. This is the condition. Okay, otherwise the system is going to get unstable. If you are not in this, if you are outside this range, your system is going to get unstable. Okay, so the controller has to be between, gain must be between 0 is -1 and 8. Actually, negative gains is not a good idea, but that's another matter. So, but it should definitely be not be less than 8. Okay.
Thank you, hocam.
Now, there is a special case. We didn't talk about it yet. What happens if one element in the first column is 0? in this case, what we do is, well, we cannot continue normally, okay? Why? Because in our regular procedure, we divide by, for example, if you have a 3 here, we divide by this term. But in order to proceed, you have to divide it by 0, which you cannot do. So in order to continue,
Hocam, but in the last one, we can have a 0. I mean, it doesn't affect our solution. The S0 part, let's say.
in the last one, yes, that doesn't matter. For example, if you had k equals 8, for example, we would have a 0 here, right? In this case, replace 0 in order to be able to continue. We do something artificial here with small, let's say positive. We assume it's positive number. Let's say call it epsilon, okay? All right. And finally, in the end, replace epsilon equals 0. Put epsilon equals 0. And then see what happens. If there is a sign change, it will still show, as we will see in the, it will show in the, let's say, root array. And we will assume that, by the way, 0 is a positive number. It's not a negative number. Let me just give you an example.
So if we have, hocam, 0 in the end, we can say that the system is stable, right?
Yes. Let's say
Thank you.
this is as follows. S to the 5 plus 3s to the 4 plus 2s cubed plus 6s squared plus 6s plus 9. For some reason, we have such a system. So s to the 5 is 1, 2, 6, 3, 6, 9. Here we have the problem, as you see. The parameters are so that it is 6 minus 6, 0, divided by 3 is 0, 0, but we will call it epsilon here, okay? The other terms, it's okay. It is 9 minus 18 divided by 3. Oh, sorry, 18 minus 9 is 18 minus 9 is 9, divided by 3 is 3. This one is 0. Okay, we proceed with epsilon now. We take this thing, 6 epsilon minus 9. So it is 6 epsilon minus 9 divided by epsilon, right? This is 9 because, yeah, 9 epsilon divided by epsilon is 9, 0. This one is complicated. Let's write it as D1 here. This is 0, so this is 0, 0. S to the 0 is, let's say, 9 times D1. This is 9. D1 is a little bit complicated, so let me write this down. Negative 9 epsilon. No, sorry, this one. 3 times 6 epsilon minus 9 and minus 9 epsilon minus 9 epsilon. Epsilon, which is 3 minus 6. These epsilons 9 epsilon squared. Okay, this is D1. Okay, I couldn't write it here, but this is D1. So if you look at the first column now, it is as follows: 1, 3, 0. This is epsilon, but you replace it by 0. Then it is minus 9 over epsilon. Okay, minus 9, yeah. 9 over epsilon. Epsilon is, 0, but if you put it here, it will be infinite. Then you have, this is epsilon squared, so it is 3 and 9. As you see here, now this is epsilon is a positive number, right? Sorry, epsilon is 0, but this minus 9 over epsilon is a negative number, right? It is very large. It's a negative number. It's negative infinity, but it doesn't matter really. So what you have here is one change of sign and another change of sign. So as you see, this was our first column.
Hocam, how do we get rid of the 6 epsilon for the
6 epsilon is 0, so it's obvious that it is 0. I just neglected it, okay? So
But-
is 9 epsilon squared, because epsilon is 0. The only problem term is this minus 9 over epsilon, but this means something very, something close to negative infinity. Okay. It is a negative number. Well, it is negative, definitely, because it's minus 9 over epsilon, and epsilon is not, negative, it is 0. Actually, we should not be doing it, but this is how this thing works.
Hocam, where did 6 go?
So we just put 0 in it. That's the case, hocam?
So 6 went to become a 0. 6 epsilon becomes a 0 when you put 0.
But it's not like, hocam, 6 epsilon minus 9 divided by epsilon. So 6 epsilon divided by epsilon makes 6.
That's what you mean. Okay.
Yes.
It doesn't matter. Yeah, you are right, actually, maybe. I should put a 6 here. Okay, 6 minus 9 over epsilon. It's still a negative number because it's very large. It is a negative number anyway. So it means that this is a system with unstable, with 2 poles, with As a last thing, let me I want to share the show this last example on MATLAB. Okay. But actually, I shouldn't be doing this, right? This is stop share. I should just share the screen. This is better. So remember that we had a system which was the numerator was 1, the denominator was 1331, and let's say k is the controller. K is, let's say, is 1 for the time being. Okay. So G is the transfer function of N and D. So this is our plot. How do we do it?
Feedback hocam. Feedback.
Excuse me?
Feedback.
Yeah, I will use feedback, but okay, I can use the following. T equals feedback of K times G and 1. But correct. Unity feedback. Okay. So the poles of T are, forward, I should say forward. It is positive, and let's look at the step response of this system. It is okay. Well, there is, and the poles are negative. Now, let's increase the K. This is 1. Let's increase it to 6, let's say. Now this system becomes like this. Its poles are, now they are getting close to the positive real axis. And if you look at the step response, now the step response becomes oscillatory, as you see. Then I'll just make K equals 8 point, well, it shouldn't be greater than 8, but let's make it 8.5, let's say. In this case, the closed loop system becomes like this. And the step response of the closed loop system now becomes, as you see, unstable. Okay. On the other hand, this is 8.5, makes the system unstable. If you make it just 8 in the limit, this is just the limit of stability. There's something wrong here. Let's make it a response for some time. As you see, it is like oscillatory. It is just in the limit of stability. It doesn't grow up, but it doesn't decay either. So this is the system response when you are in the limit of stability, K equals 8. Okay, and we could predict this by using the Routh array. Okay. Looking at the system gain, looking at the Routh array, we could predict that when K is equal to 8, the system will be at the limit of stability, any value greater than 8 will produce a unstable system. That's what we could find.
Hocam, may I ask something from the MATLAB thing?
Yes.
So to define the stable interval, let's say the interval gain stability for Türkçe sorsam olur mu hocam? Kafam biraz durdu da. Şeyi yani gain'de mesela bir çözdüğünüz bir verdiğiniz example'da -1 ile 8 arasında dedik 50 çözüp. Peki MATLAB'da bunu bulmak için böyle iterasyon mu yapmamız lazım sürekli yoksa önce bir 50 çözmemiz, bir gain interval bulmamız sonra o aralıkta mı çalışmamız lazım?
Well, it is always better if you can find an analytical solution. This trial and error is, it's not neither elegant, it's not an elegant solution. Plus, it's too time consuming. If you can find a solution which definitely tells you that you have to be between this and that value, then you don't have to do iterations or anything. It's a better way of doing things. If you can find an analytical solution, that's always better.
Hocam. Thank you.
Okay.